Okay, good morning, afternoon, everyone. Today I'm going to present a paper titled Membership Inference Attacks Against Large Vision Language Models. This work was conducted by researchers or students group at EPFL in Switzerland. And the paper was accepted at NeurIPS 2024. This research addresses critical privacy concerns in more modern vision language model by investigating how attackers can detect whether specific data was used during model training. Let's dive into the details. Before we begin, let me give you a quick overview of what we'll cover today. First, I will provide an introduction to vision language models and privacy concerns they raise. Then we will review the background and related work on membership inference attack. Next, I'll explain the methodology proposed in this paper, including their novel cross-modal attack pipeline. After that, we'll look at how they constructed the VLMIA benchmark, which is the first standardized dataset for evaluating membership inference attacks on vision language models. Then we'll examine the experimental results on various models, including LLaVA, InstructBLIP, and even GPT-4. We will discuss the implications and limitations, and finally conclude with the key takeaways from this work. In recent years, let's start with some background on VLM. In recent years, we have witnessed the rise of large vision language models, or VLMs for short. These include well-known models like GPT-4, uh, Gemini, and LLaVA. These models can process both images and text, giving them multimodal capabilities. They are being used for various applications such as image captioning, where the model describes what's in an image, visual question answering, where users can ask questions about images, and image knowledge extraction. However, with these powerful capabilities come significant privacy concerns. The training data for these models may contain sensitive information, such as private photographs or medical diagnostic records. This is particularly worrying because previous research has shown that machine learning models can memorize and leak the training data. So if someone's private medical scan was used to train a model, there's a risk that information could be exposed. This diagram illustrates the concept we are dealing with, the intersection of vision and language in these large models and the privacy risk that come with it. This brings us to the concept of membership inference attacks, or MIA. So what exactly is a membership inference attack? In simple terms, it's a method to determine whether a specific data sample was part of a model's training dataset. This is important for two main reasons. First, it helps protect privacy by detecting if sensitive data was inappropriately used. And second, it helps detect test data contamination, which is crucial for ensuring the validity of model evaluations. However, applying MIAs to vision language models present several unique challenges. First, and this is highlighted in red, there's no standardized benchmark for evaluating an MIA method on VLLMs. Without this, it's difficult to compare different attack strategies or measure progress in the field. Second, we have the multimodality detection problem. Previous work on multimodal models like CLIP focused on detecting image text pairs, But in practice, we need to detect individual images or tags. For example, you might want to know if a specific photograph was used in training, regardless what tags it was paired with. Third, we need target-free methods in VLLMs. We can only access image embeddings, not the actual image tokens. This means traditional target-based attack methods, which rely on knowing the ground truth tokens, won't work. We need approaches that can work with just the embeddings. So, given these challenges, this paper makes four main contributions. First, they create the first MIM benchmark specifically tailored for various VLLMs. This benchmark, called VLMIA, provides standardized datasets for evaluating membership inference attacks. Second, they propose a novel MIA pipeline for token level image detection in VLLMs. This is significant this is significant because it allows detecting individual images rather than image text pairs. Third, they introduce a new metric called MaxRényi-K, which is based on the model's output confidence. This metric is flexible and can be applied to both text and image data. Fourth, their approach works for modalities. For both modalities, you can detect whether text or images were in the training dataset. All their code and datasets are publicly available at the GitHub repository, which should be available for future research in this area. To understand their approach, let's first review the two main categories of membership inference attack. Target-based MIA methods use the next token as a target. They compute the prediction probability for this non-target token. Example includes minimum K% and perplexity metrics. However, there's a problem with these methods for VLLMs. They require token level access to the data. For images, we don't have discrete tokens in the same way we do for text, so these methods can be directly applied. Target-free MIA methods, on the other hand, don't need a specific target. Instead, they use the anti-probability distribution over possible outputs. They can work with embeddings rather than discrete tokens. This makes them the solution for VLLMs, where we only have access to image embeddings, not tokens. Here's the key insight. For VLLMs, we only have access to image embeddings, not image tokens. Therefore, target-free methods are essential. This is one of the main motivations for the approach proposed in this paper. Let's briefly review the most relevant previous work in this area. Ko and colleagues in 2023 performed membership inference attacks on CLIP, which is a contrastive vision language model. However, their approach could only detect image text pair whether a specific image paired with a specific text was in the training set. Additionally, their method was limited to contrastive models like CLIP and doesn't extend to generative VLLMs. In contrast, this current work focuses on membership inference attacks on generative VLLMs. Importantly, it can detect individual images or tags, not just pairs. The methods work with models like LLaVA, InstructBLIP, and even GPT-4, this is a more practical real-world scenario because in practice, you typically want to know if a specific image was used in training, regardless of what caption or text it might have been paired with. Now let's formally define the problem the problem they are trying to solve. In their setup, they have a VLLM model. They have a VLLM model denoted A theta, which maps an image X and an instruction I to output text Y. For example, the instruction might be describe this image concisely, and the output Y would be the generated description. They also have two datasets, a member set which contains data that was used in training, and a non-member set which contains similar data that was not used in training. The goal is to design a scoring function S which takes an image X and an instruction I as input. This function should produce a high score when X is a member of the training set and a low score where X is a non-member. They evaluate they evaluate their method using the area under the ROC curve or AUC. An AUC of 0.5 means random guessing, while an AUC of 1.0 means perfect detection. Higher is better. Here's the key innovation of their approach: the cross-modal MIA pipeline. This diagram illustrates how they convert an image membership inference problem into a text membership inference problem. This is clever because we have well-established text-based MIA methods, but image-based MIA on VLLMs is challenging due to the lack of discrete tokens. The pipeline works in three steps. First, they generate a text description from the image using the VLLM. For example, they might prompt the model with describe this image concisely. Second, they apply text-based MIA metrics on the generated description. This could be metrics like perplexity or their proposed MaxRényi metrics. Third, they use the model's confidence in the generation as a signal for membership. The intuition is that if the model has seen an image during training, it will be more confident when generating description of that image. This cross-modal approach is particularly elegant because it leverages the generative capabilities of VLLMs to bridge the gap between image and text modalities. Now let's look at the proposed method in detail. Max I just call it MaxR, okay? The method is based on Rényi divergence for a sequence Y consisting of tokens Y minus 1 through Y minus T generated by the model. They compute the Rényi divergence with parameter alpha. This formula takes the sum of the token probabilities raised to the power alpha, takes the logarithm and divides by 1 minus alpha. The key component is P of yt given x, I, and the previous tokens. This is the probability the model is assigned to each tokens in the sequence. The MaxRényi sorry Rényi whatever. Okay. The MaxRK variant applies this R computation to only the top K% of highest probability tokens. This helps focus on the most confident predictions. The alpha parameters controls how the method weighs weighs different probabilities. When alpha equals 0.5, it gives more weight to low probability tokens. When alpha equals 1, this reduces to standard Shannon entropy. When alpha approaches infinity, it focuses only on the highest probability token. This is essentially equivalent to existing method like min k% and perplexity. The intuition behind this method is straightforward. If an image was in the training set, the model should be more confident when generating descriptions of it, resulting in higher token probabilities and thus different R divergence score. Let's compare the different methods available for membership inference attacks. The table summarizes the key methods. Perplexity and min k% are both target-based methods. They require knowing the ground truth next token. Lowercase and zlib are target-free methods that don't need this information, and their proposed maxr is also target-free. maxr has several advantages over existing methods. First, it works without knowing the ground truth tokens. This is crucial for image data where we don't have discrete tokens in the traditional sense. Second, it has a flexible alpha parameter. By tuning alpha, you can adjust the method's sensitivity to different parts of the probability distributions. This flexibility shows the method to adopt to different scenarios. Third, the k% parameters allows focusing on the most confident predictions. You might use the top 10% most confident tokens, for instance, which can improve signal to noise ratio. These properties make maxR particularly well suited for membership inference in vision language models. Before we look at the result, it is important to understand why creating a benchmark for VLLM membership inference is so challenging. Why is this difficult? Well, first, VLLMs are trained on massive, diverse datasets. We are talking about millions of images and text from various sources. Second, different models use different training pipelines. LLaVA, InstructBLIP, and other models all have their own unique training procedures. Third, and most importantly, we need ground truth labels. We need to know with certainty which data was used in training and which wasn't. Their solution is to create a controlled benchmark using several strategies. First, they use public datasets with known training and test split. For example, if a model was trained on Flickr 8K, they can use Flickr 30K images as non-members, since we know those were not in the training set. Second, they leverage temporal information. For instance, Wikipedia articles can be split by timestamp. Older articles were likely used in training, while very recent articles almost certainly weren't. Third, they create synthetic member data through fine-tuning. They can fine-tune a model on specific data and then test whether the membership inference methods can detect that data. These strategies allow them to create a benchmark where they have reliable ground truth labels. Here's an overview of their VLMIM benchmark. This figure shows examples from their benchmark. You can see different types of data and how they are processed through the pipeline. This figure shows example from their benchmark, and the benchmark consists of three main data set type. First, VLMIM Flickr use real Flickr 8K images, which were actually used in LLaVA's training data set. The non-memberships comes from Flickr 30K, which were not used in training. This gives us a real-world test case. Second, VLMIA text consists of synthetic instruction tuning text. These are text-only data, and during the instruction fine-tuning phase of VLLM training. Third, VLMIA DALL-E use AI-generated images from DALL-E 3, which was released in 2024. Since GPT-4 Vision was trained in 2023, these images definitely were not in its training dataset, making them reliable non-members for testing GPT-4. This diverse benchmarks allows testing membership inference across different modalities and different types of training datasets. Let me give you some specific details about each dataset. Looking at this table, we can see the structure of each dataset. VLMIA Flickr focuses on the image modality. The members are from Flickr 8K and non-members from Flickr 30K. This gives us thousands of real photographs to test with. VLMIA text is text only. Members consist of instruction data used in fine-tuning, while non-members are newly generated text that follow similar patterns but were not in the training set. VLMIA DALL-E is also image modality, but uniquely it only has non-members. These are DALL-E 3 generated images from 2024, which are guaranteed not to be in GPT-4's training dataset since it was trained earlier. They also use WikiMIA, an existing benchmark for large language models, which split Wikipedia articles by timestamp, early articles as members, recent ones as non-members. The benchmark has several important properties. The member and non-member splits are balanced to avoid bias. They test multiple text lengths 32, 64, 128, and 256 tokens to see how length affects detection, and the visual content is diverse, covering various scenes, object, and context. Now let's look at the experimental results, starting with image membership inference on LLaVA. The key findings are quite striking. The MaxR method with alpha values of 0.5, 1, and 2 achieves the best performance, specifically using the top 10% of tokens, what they call max 10% works best. This significantly outperforms baseline methods, achieving AUCs up to 0.75 and higher on the VLMIA Flickr dataset. Looking at these specific numbers, we can see that Perplexity, a traditional method, achieves an AUC of 0.57 minimum K%. Another baseline gets 0.61, but their MaxR 10% methods with different alpha values perform much better. 0.76 for alpha equals 0.5, 0.75 for alpha equals 1, and 0.74 for alpha equals 2. This is a substantial improvement, going from around 0.6 AUC to 0.75 AUC represents a major increase in detection capability. An AUC of 0.75 means the method can correctly distinguish members from non-members 75% better than random guessing, which is quite significant for a privacy attack. The results for tax membership inference are particularly interesting because they reveal different patterns depending on when the text data was used in training. For instruction tuning text, that is, text used in the recent fine-tuning stage, target-based methods performs better. This includes Perplexity and Min-K. Why? Because this data was seen recently in training. The model still has strong memory of specific next token patterns. For VLA, for LLM pre-training text used much earlier in the base language model training. Target-free methods are better. Specifically, MaxR with large alpha values performs best. This is because the model's parameters have changed significantly since seeing this data during fine-tuning. The numbers confirmed this. For instruction tuning, Perplexity get 0.638 and Min-K achieves 0.763. For LLM pre-training, their max 0 method, which is MaxR with alpha approaching infinity, achieves 0.688. The key insight here is that method choice depends on training stage. If you are trying to detect data from recent fine-tuning, use target-based methods. If you are detecting data from earlier training stages where the model has changed a lot, use target-free methods like MaxR. This is an important practical finding for everyone conducting membership inference attacks. One of the most surprising results in this paper is the effectiveness of membership inference attacks on GPT-4, which is a closed source model. Let me explain the setup first. They use GPT-4 Vision Preview API, which provides limited access, specifically only the top 5 token probabilities at each position. They couldn't get the full probability distribution. To work around this, they made a uniform distribution assumption for the remaining tokens, assuming there are about 32,000 tokens total in the vocabulary. Now look at these results. On the Dolly dataset, there are methods with alpha equals 0.5 achieved an AUC of 0.8 That's over 81%. Even Perplexity ZLib baseline gets 0.807. On the Flickr dataset, they achieved 0.63. This is quite surprising and concerning, even with a closed source model where they only have API access and limited probability information. They can still perform highly effective membership inference attacks. An AUC of 0.815 means they can detect training data with high reliability. The privacy risks here are significant. Even commercial models with restricted API access aren't safe from membership inference. This highlights the need for stronger privacy preserving techniques in VLLM training. Now let's look at some ablation studies to better understand what factors affect the attack's effectiveness. This graph shows how the length of the generated description affects MIA performance. They varied the max new tokens parameter from 32 to 256 tokens. The findings are interesting as the description length increases, the AUC of the membership inference attack also increases. However, this improvement plateaus when max new tokens reaches 128. Why does this happen? Well, shorter descriptions don't contain enough information about the image to effectively distinguish memberships from non-members, but excessively long descriptions also don't help because the tokens generated later in the sequence tend to be more genetic, generic. They are less closely related to the specific image and more about general conversational patterns. So there's a sweet spot around 128 tokens where you get enough descriptive information without diluting the signal with generic tokens. This is a useful finding for practitioners. You don't need extremely long description, and in fact, they might even hurt performance. Another important question is whether membership inference still works on corrupted versions of the training images. The graph shows the results of the corruption experiment. They applied four types of corruption from ImageNet-C: snow, brightness changes, JPEG compression, and motion blur. Each corruption type has three severity levels: marginal, moderate, and severe. The dotted line shows the baseline performance on uncorrupted images. Several interesting patterns emerge. First, corrupted member images do make MIA more difficult. As expected, the AUC drops below the baseline. However, the attacks can still be successful even with corruption. Second, not all corruption affect MIA equally. Reducing image quality through JPEG compression or adding motion blur degrades MIA performance more significantly than changing the brightness or overlaying snow texture. This makes intuitive sense. Compression and blur actually remove or distort visual information, while brightness changes and snow overlays preserve most of the underlying structure that the model might have memorized. From a privacy perspective, this is concerning. Even if images are somewhat corrupted or modified, they can still be detected as training dataset. Simple transformations are not sufficient to protect privacy. Let's synthesize the key insights from all these experiments. First, regarding methods selection, you should use target-based methods like perplexity and mean-K when you are trying to detect data from recent fine-tuning, but use target-free methods like MaxR when the model has undergone significant changes after seeing the data. Why this difference? Recent fine-tuning means the model still has strong associations between specific tokens in the sequence. Target-based methods exploit this, but after major model changes, the specific token level patterns may be disrupted, and methods that look at the overall probability distribution become more robust. Second, cross-modal attacks are effective. Converting image MIA to text MIA worked well across different VLLMs. The key insight is that generated descriptions carry a membership signal. The models generate more confident specific description for images it has seen during training. This cross-modal approach successfully works across different VLLM architectures, including LLaVA and InstructBLIP, showing as a general technique rather than model-specific. These results have serious privacy implications that we need to discuss. First, even closed source models like GPT-4 are vulnerable to membership inference attacks. You might think that keeping the model weights private would provide protection, but it doesn't. Second, limited API access is still sufficient for effective attacks. Even with only the top 5 token probabilities, attackers achieved over 80% AUC. You don't need full model access. Third, corrupted images can still be detected. Simple transformations like compression or blur don't fully protect privacy. Fourth, the success rate are concerningly high, in some cases exceeding 0.8 AUC. This isn't a theoretical vulnerability, it's a practical exploitable weakness. Given these risks, what should be done? First, we need stronger privacy preserving training techniques. The current approaches aren't sufficient. Second, differential privacy needs to be adopted and adapted and applied to VLLMs. This is an active research area but needs more attention. Third, careful data curation and licensing is essential. Organizations need to ensure that they have proper rights to use training data and inform data subjects about their risks. Fourth, regular privacy audit or audit using MIA benchmarks like this one should become standard practice. Just as we test models for performance, we should test them for privacy leakage. Like any research, this work has limitations that are important to acknowledge. First, the benchmark scope is limited to specific VLLMs and datasets. They tested LLaVA, InstructBLIP, and GPT-4, but there are many other vision language models out there. We don't know if these findings are generalized to all VLLMs. Second, they assume a black box setting where attackers don't have access to model internals. If attackers do have white box access, they might be able to perform even more effective attacks. Third, there computational cost to this approach. You need to generate description for each test image, which requires multiple forward passes through the model. This might be prohibitive for very large scale attacks. Fourth, there's some instruction sensitivity. Performance can vary depending on the exact prompt used. The paper shows it works across different prompts, but careful prompt engineering might improve or degrade attack effectiveness. Fifth, they haven't tested on continuously updating models. Modern systems are often fine tuned regularly with new data. How membership inference performs in this dynamic setting is an open question. Future works should extend this to more VLLMs like Gemini or Cloud, develop defense mechanisms against these attacks, and explore more sophisticated attack strategies that might even more effective. Let me summarize. Um, the main contributions of this paper. First, they created the first comprehensive MIA benchmark specifically for VLLMs called VLMIA. This provides standardized datasets and evaluation protocols that the community can use. Second, they propose two novel cross-modal attacks pipeline that converts image membership detection into a text-based problem. This elegantly solves the challenge of not having discrete image tokens. Third, they introduced the MaxR metric based on R divergence. This is a flexible, theoretically grounded metric that can be tuned with the alpha parameter for different scenarios. Fourth, they conducted extensive evaluation on multiple models, LLaVA in different sizes, InstructBLIP, and even GPT-4. The consistency of the results across models suggests their findings are robust. The impact of this work is significant. It advances our understanding of privacy risk in VLLMs. It provides practical tools for detecting training data misuse, which is important for both defenders and auditors. It established a foundation that future MIA research can build upon, and importantly, they have made their code and dataset open source, which will accelerate research in this area. As we conclude, I want to emphasize four key takeaways messages. First, VLLMs are vulnerable to membership inverse attacks. This isn't a theoretical concern, it is demonstrated reality with high success rate. Second, cross-modal attacks from image to text are effective. You don't need direct access to image tokens. The generated descriptions leak sufficient information about membership. Third, even closed source models with limited API access are at risk. Restricting access to model rates or limiting API responses is not sufficient protection. Fourth, method selection matters. You need to choose your attack method based on the training stage and how much the model has changed since seeing the data. The bottom line is clear. Privacy protection in VLLMs requires serious attention. This isn't something that can be ignored or addressed with simple fixes. It requires fundamental changes in how we train and deploy these models. Thank you very much for your attention. I hope this presentation has given you a clear understanding of membership inference attacks on vision language models and why they matter. Again, all the codes and datasets are available at this GitHub repository if you want to explore further or build on this work. The The full paper is available in the NeurIPS 2024 proceedings. I'll be happy to take any question you might have about this methodology, the results, or the implication of this work. Thank you once again for attention.